Hi, my name is Yunsi Chong and I'm a PhD student at MIT. I'll give a brief presentation on my research that greatly benefited from supercloud computing resources. The title of my presentation is Machine Learning Model for Predicting Kinetic Solvent Effect. Many reactions that are important to environment and industry happen in liquid phase, such as atmospheric aerosol chemistry, organic synthesis, and drug degradation. Solvents can have significant effects on rate of many neutral and free radical reactions, and accurately predicting this solvent kinetic effect is necessary in order to understand underlying chemistry behind important kinetic mechanisms. To give a brief background on kinetic solvent effects, here the diagram shows the potential energy surface of a reaction that happens in gas phase. The reaction has certain activation barrier height, and when the same reaction happens in liquid phase, solvent can stabilize the transition state and reactant by different magnitude, making the activation barrier to change. And this change in activation barrier in liquid can be represented using delta delta G solve here, which is defined by the solvation free energy difference between transition state and reactant. And this delta delta G solve value can be directly used to relate gas phase rate constant to liquid phase rate constant. Currently, there are some methods to predict gas phase rate constant in a fast manner. However, there is no current model to give a fast prediction of delta delta G solve, which motivated me to conduct this research. And here's a methodology for developing a predictive model for this work. First, in order to generate data, I first calculated delta delta G solve and delta delta H solve values for reaction in common solvents at 298 Kelvin using the Cosmo-RS method based on the Granville and Harms reaction data sets. This includes a total of around 28,000 reactions in 295 solvents, which amount to around 8.4 million Cosmo-RS calculations that are performed on SuperCloud. And the Cosmo-RS method was used because it is known to provide accurate prediction of delta delta G solve value with the mean absolute error of about 0.3 kcal per mole. Next, after generating a massive set of delta delta G solve and delta delta H solve data, we then train a machine learning model to predict this value from only reaction and solvent smiles. And for performing hyperparameter optimization and training machine learning model, we use supercloud GPU computing nodes. And finally, with the final machine learning model, we tested it on unseen reaction to evaluate its predictive accuracy. And here is a diagram of machine learning architecture used for this work for predicting the value for a reaction in a solvent. This model uses DMPNN, which stands for Directed Message Passing Neural Network, and it has two different DMPNN network to first encoding reaction smile string into reaction embedding, and for encoding solvent smile to solvent embedding. And these embeddings are concatenated together and fed toward neural network to give a prediction of delta delta G solve and delta delta H solve value. And this is the final result for the machine learning model performance on unseen reaction test set. So these reactions were withheld from the training set for machine learning model, and then the model was tested on this reaction. And the left figure shows the value on the prediction on delta delta G solve, and the right gives a prediction for delta delta H solve. This is a parity plot showing prediction on the y-axis and the actual value at the x-axis. And then we can see that overall the predictions lie close to the parity line, which shows a great predictive performance. And for delta delta G solve, we were able to reach mean absolute error of about 0.71 kcal per mole, which is below 1 kcal per mole. And the typical computational accuracy tend to be about 1 kcal per mole. So when we reach below that, that shows our machine learning model gives very good prediction. And we also tested our model on reactions that are much larger than the reaction found in our training set, and then we found that the model still shows very great performance on this. So with that, I would like to thank my advisor, Professor William Green, and our Green Group members. And and most importantly, I really like to thank MIT SuperCloud team for providing awesome computing resources like CPU and GPU that enable us to perform millions of computational jobs and train machine learning model with very large training sets, and also for providing great advice on how to improve the computational workflow, and also for excellent maintenance of the server. Thank you so much.